All right. Hi, everybody. Welcome back to our office hours for the week. I hope you can all hear me okay and see all this okay. Can someone just give me a thumbs up that the audio is working in the chat box? Just to make sure or something. Perfect. All right, so we're just going to go over some of these warm-up questions just to kind of review what we talked about last class. As you can tell, the material is very different from the first half of this class, so definitely pay attention here because it becomes more like mechanistic, more intuitive, I guess you would say, in terms of how rigorous the old material was. Okay, so the first thing is classify the molecules A through D at the position indicated with an arrow as either a nucleophile or an electrophile. So we have to remember what those words mean. Okay, so let's write over here that nucleophile equals nucleus loving. Okay, so we know nucleus, and I'll put a heart, nucleus loving. Okay, so if it loves the nucleus, that means it likes a positive center. So what likes positive things? Negative things. So it has lone pairs. Okay, so it has some sort of lone pair, or other electron density that adds into some sort of deficiency, okay? So nucleophiles like the nucleus, they have lone pair or other electron density that wants to donate. Okay, so then you can rationalize what an electrophile is. So an electrophile is electron loving. So electron loving. So what likes electrons? Well, that's something that would be positive. Okay, so a deficiency. So has some positive deficiency. So we know one example of that so far. Actually, we know two of those, deficiency. And one of them is a carbocation. So something like, that, because that's a deficiency, would want electrons. Or, we have another example, maybe like an alkyl halide, where a dipole moment is permanently localized toward that halogen, resulting in a slight positive deficiency on an adjacent carbon. Okay, so, hopefully that clarifies what a nucleophile and electrophile is. It's very important. It's going to be, a concept that we revisit for the remainder of the year, or the term. Okay, so let's look at these positions that are indicated with an arrow. So if you look at A, structure A, with that arrow pointing at that carbon of the carbonyl, we know that there's a localized dipole moment towards that oxygen, which makes that carbon partially positive. Well, a partially positive carbon, we said, would be electrophilic. It wants electrons to fix that deficiency. So we would classify this thing as an electrophile. Okay. And then for B, we kind of just showed that example over here with that alkyl bromide, but we have another localized dipole moment towards that chlorine, resulting in a partially positive, carbon next to that chlorine. So that would make this an electrophile as well. Okay. So water at this oxygen position has lone pairs, okay? Those lone pairs can add probably into some sort of deficiency. So I would call that a nucleophile. There's lone pairs, there's electrons present. It wants to give them off to something. And the same thing for chlorine. So if you didn't know, maybe in step 2, you would see that, this reaction is similar. Step 2 of this reaction would kind of give it away, but this is a nucleophile. And the same logic applies, that it's a source of electrons to donate into a ring or donate into a deficiency. So that's it. Any questions on 1? All right. So for 2, 2 was our first reaction that we did, and we also covered the concept of regioselectivity. So I'm going to write that out here. So regioselectivity was kind of this big concept yesterday. And we also talked about a little bit of stereochemistry or stereoselectivity. And we also talked about, let's just say, Markovnikov. Okay, so Markovnikov's rule was this rule of regioselectivity, which talks about, when we have a difference in substitution. So by difference, I mean here at this, carbon of the pi bond, I see I have a benzene ring and a methyl group, where at this side of this carbon-carbon double bond, I just have a methyl group. So clearly there's a difference in substitution going on. And what that means is what Markovnikov's rule, or the regioselectivity rule, says is that when doing this type of reaction, the hydrogen is going to add to the less substituted position of the alkene to yield a carbocation that is on the more substituted position. And we were like, why does a carbocation on a more substituted position become favorable? And it has to do with hyperconjugation. So I'll write that down here again. So I'm not going to go over all these trends again. You can watch that video, but just keep this all in the back of your head. Hyperconjugation was the reason of Markovnikov's regioselectivity rule. The more substituted that carbocation is, the more stabilized it is via partial donation of these alkyl groups that are adjacent. Okay, so let's draw this mechanism just to, bring it back to our memory. It's always source to sink. So it's the nucleophilic pi bond with 4 electrons in it that grabs this hydrogen, because remember, it's an electrophile at that position. And since, we can only have 2 electrons bounded to hydrogen, we have to break a subsequent bonds. That's why there's this other arrow here. And then, the result of that step would be a structure that looks like this. This is our intermediate. And we added the hydrogen to the less substituted side, and we generated free iodide. Okay, so that is the intermediates of step 1. Then we know we have one more step to go, where that iodine nucleophile, that's why I said that for structure D up top, is going to add into that deficiency to yield this structure. Okay, so watch out. Did I generate a new chiral center? And yes, I did. Remember, talk about that whole structure of what a carbocation is, and we said it was an sp2 center with unhybridized p. So we're just bringing all this back, unhybridized p. So that unhybridized p orbital, I could either attack to the front face to make a wedge. So that would have been maybe something like that wedged iodine but dashed methyl group, or it could have attacked from the back face. Okay, so that could have led to a dashed iodine, which causes that methyl group to become a wedge. Okay, so that's pretty much all we talked about last class. It was a lot of things, so I'm not kind of diminishing that, but this is the good summary of what we talked about. So does anybody have any questions going into today's material? All right, so let's just go to the workbook. We're going to go to page 59 right now. So this is carbocation stability, or rearrangements, I should say. And we have a question. Where did the H go in the intermediate? Good question. So I'll bring that back. So where did the H go in the intermediate? So you can tell that we have a choice. This is the region or regioselectivity rule. And we have this region, the more substituted position, or this region, the less substituted position. So the hydrogen is always going to add to the less substituted side in this reaction. So you can tell, let's call this, maybe position A and position B. The hydrogen is adding to position B. So you look over here, hydrogen is at position B. And then same thing, I didn't draw it in because you don't have to draw hydrogens in line angle, but all of these structures, the hydrogen is on position B. Okay, so I hope that kind of clarifies what's going on. All right, let's go to carbocation rearrangements. So we didn't talk about this yesterday, and all the examples that we did yesterday didn't involve carbocation rearrangements. So we're actually on page 60. I guess that's the first example of it. And what it is the driving force for this is, when you first generate a carbocation, based on the regioselectivity rule, there could actually be another step of internal rearrangement in these molecules to make an even more stable intermediate, which is weird. Like, why would a molecule internally rearrange? I've never heard of that before. That's kind of bizarre. But it does happen, and it happens a lot of the time. And I think I'm going to do this on a separate sheet of paper first, and we can jump into these examples in a second. So here's the logic behind that. So let's say, I'm doing that same reaction before. And I'm actually going to use, there's a reason why I chose this example to start with. Let's do, okay, so we're going to do this structure, and we're going to do HCl. So this is just a plain example right now. So the same exact mechanistic steps are going to happen. So we're going to have, this nucleophilic pi bond, grab that electrophilic hydrogen. Then you have to do one more step because you don't want to exceed the octet. So we generated the chloride anion. So let's just draw that intermediate and isolate it. So it's this kind of structure. So where is my carbocation going to go? Remember, it's on the more substituted position of that pi bond, and I added that hydrogen here. Okay, so and then we also have kind of this free chloride hanging out. Okay, so right now we see that we have what type of carbocation? Well, if I were to classify this, I see that there's one group attached to it, another group attached to it. So let's call this a secondary carbocation. Secondary. But there's one more mechanistic step that actually does happen before you get the part. If you were to just add chlorine right here, it'd be wrong. So what happens is that we actually have, and I'll draw this maybe in green, we have this hydrogen right here. Okay, and this hydrogen can literally shift over. It's so close by in the form of a hydride. Okay, so what hydride is H, a lone pair, and a negative. That's what hydride is. So you can imagine these two electrons that are in this hydrogen bond are literally going to shift over. And this is the arrow you would draw. You don't have to draw these electrons, but you would just draw an arrow from that hydrogen to that deficiency. The resulting structure from that, I shouldn't draw resonance arrows, would be, keep that hydrogen there, and I'll draw this new hydrogen in the screen. And then now the carbocation, you can tell, shift from that secondary position to a tertiary position. So now this is a tertiary carbocation. So clearly this carbocation is definitely more stable than this one for reasons we talked about yesterday with hyperconjugation. So this would be the intermediate that we isolated. Okay, this is what we want. So then the chlorine attacks in this situation, okay, and that generates these structures. Again, we would have a racemic mixture here for all the reasons we talked about before and in the warm-up with the unhybridized p orbital. Okay, and those would be our products. So notice, even though our pi bond was, terminal at this point, which, and you would expect out of the primary or the secondary position, that the secondary position was going to have the chloride, there was actually an internal rearrangement that made the tertiary position the better position to add that nucleophile. Okay, and this does happen. So anytime that we have, carbocations in our reaction, and there are going to be some where we don't and some that we do, we always have to check for these kind of shifts. Okay, so now one more thing I want to comment about. So if I, let's say, were to change this one and I would add another methyl group here, okay, instead of that hydrogen, then I wouldn't be able to move hydrogens because there aren't any hydrogens here. So what you would have to do is use a methyl group, and you can move this methyl group, and it's called an alkyl shift instead of a hydride shift. This hydride would just be hydrogen. And an alkyl shift would move this methyl group over one position. So the structure, I'm gonna do that quickly, would be, something that looks like, this would be my intermediate because this group would have moved over there. Remember there would have been a positive and that would have moved over instead of the hydrogen. And then your chlorine would have attacked there. So it would have been okay. So what I want to say essentially is that it's easier to do a hydride shift because it's a single atom than to do an alkyl shift. So clearly with the original example, that's why I chose to move the hydrogen and not the methyl group, because it's so much easier just to move a single atom than to move a whole group of atoms. But when you don't have a choice, you can't help it and you have to move the methyl group over. Okay, so these are the two types of shifts. So we're going to call them the 1,2 hydride shift. And these are the only two that exist. The 1,2 hydride shift or the 1,2 alkyl shift. And why do I have 1,2? Well, because it's going from the 1 position to the 2 position, the 1 position to the 2 position. I'm not naming it based on nomenclature, but I'm just naming it in the sense of, where that transition was going. It's going from the 1 carbon to the next one. Kind of like the same thing with the 1,3 diaxial interactions. That's how the naming convention is derived. 1,2 is moved to an adjacent position. Any questions on these type of shifts? I know we didn't kind of talk about this yesterday. None of our reactions had these in them yesterday, but we're going to pick them up now. Okay. And then there's one more type of rearrangement that can occur. So these are the two, shifts that occur, but there's a different type of rearrangement, and that's called a ring expansion. Okay, so ring expansions. So these happen with, unideal cyclic structures. So let's say, maybe let's do cyclobutane. Okay. So we have maybe a structure like this, and we are going to react it with HBr. Okay, so let's just do everything that I normally would have done before. So nucleophilic pi bond, grabbing that electrophilic proton, this electron density staying on that bromine, and that results in this intermediate. Okay, so remember, I added the hydrogen to the less substituted side, which makes the carbocation on the more substituted side. Don't forget I have free bromide hanging out. Okay, but the bromide isn't going to just attack, and notice I'm not going to do a hydride or alkyl shift because I don't have any of those next door to really move around. It's not going to influence the stability. But what is a bigger driving force is, breaking this ring open. And why would I want to break that ring? Well, remember, what is this? What is this center? The center has 2 hydrogens here. Okay, so that would make this carbon an sp3 center. So all of these centers are sp3 hybrids. Okay, so in the sp3 hybrids, what's my predicted bond angle? Well, my predicted bond angle is 109.5. Okay, so what is the bond angles in a square? 90 degrees, right? So 90-degree bond angles significantly deviate by almost 20 degrees from what the ideal value would be. So this is a very, very strained, unstable structure. So it's better to, make a 4-membered ring a 5-membered ring, or a 5-membered ring a 6-membered ring. Remember, 6 is our goal, because those 6-membered rings can do something, you're gonna hate me, chair conformers. And that was the whole logic of why we did chair conformers, because these, cyclohexane structures can form this kind of conformer, which is close to 109.5. But any other cyclic structure that isn't 109.5 is going to have some significant ring strain. So I'm going to write that. Ring strain. That's the term we use, ring strain. Okay? So this is going to be our expansion. I'm going to redraw that intermediate so I have more space over here and talk about this expansion. Okay. So let's do this. Let me number this as 1. This is a very visual thing. And let's call that 6. Okay, so these are all my carbons. 1, 2, 3, 4, 5, 6. Okay, so what's going to happen is I'm going to literally cut this bond. And instead of it being attached, so instead of the electrons being shared from 5 to 2, I want to share the electrons between 5 and 1. Okay, so what that means is I'm going to draw an arrow from 5 to 1. Okay, so let me draw this again in a different way. So this, maybe you guys can see this now. Okay, so that's what I basically did in the structure, and I'll bring my numbers back. 6. I know some of you guys might already know all this, but it's really worth the time of going through it again. Okay, so notice how I removed that, and I want to put these 2 electrons that are in here to carbon number 1 and fix that deficiency. So now you might see, I'm going to draw this line, okay? So now do you see how that's 1, 2, 3, 4, 5 total carbons? Aha. So now we made a 5-carbon ring from that 4-carbon ring. Okay. And let's keep my numbering right. So we have, just a methyl group. Let's keep our numbering. So that's 6. This is 1, 2, 3, 4, 5. So notice that I took electrons away from carbon 2. So that's where my new carbocation is going to be placed. Okay. So remember, we fixed the carbocation at 1 by removing these electrons from in between 2 and 5 and putting it on 1. So there's no carbocation on 1 anymore. What happened was, though, is I did break this bond at 2. So now 2 is electron deficient. Okay. So that's the ring expansion. And then we can say we have free bromide. Okay. And that bromide is going to attack at that position. And that results in this structure. Okay. So now we're going to bring back this logic. How many stereocenters do I have? Well, I definitely have one here. I definitely have a second one here. So I have 2 stereocenters. Let's bring back that equation. 2 to the n, where n is the number of chiral centers, equals the number of stereoisomers. Okay, so that's 2 squared. That gives me 4 total stereoisomers. So I would be expected to draw on a test, or on a predict, like, all the ones that apply. Wedge, wedge, dash, dash. You just try all the combos. Wedge, dash, and dash, wedge. And those are your 4 major stereoisomers. Okay, so that is your 3 types of rearrangements. Okay, 1,2 alkyl shift, pretty easy to spot. 1,2 hydride shift, or ring expansions. So let's just kind of draw a line there. That's ring expansions. Okay, I know it's very scary at first, but you're going to do this so often that you're going to spot it every time. Okay, this isn't going anywhere. It's going to come back in Orgo too. So make sure that you always, whenever you see a carbocation, ask yourself, is there any rearrangements that could happen to make it better? One thing I want to comment on before I move on is that when we're at this position, some of you might be asking yourselves, why didn't I do another rearrangement? Why didn't I go from this secondary carbocation and move maybe a hydride over to get to that tertiary position? And you know, you can arguably say that maybe that does happen, but for the purposes of your Organic 1 class and also Dr. Habenick as well, you do one rearrangement only, okay? So if I saw a ring expansion, I want to do the ring expansion, and that's drawing the products from that, okay? Like, yeah, someone might argue you might have a minor product, you know, at that position. And I think sometimes in the keys, well, like at least for my book, like I did multiple expansions, but I think Dr. Peterson at least went back into the key and wrote assume one rearrangement, okay? So for your purposes, don't worry about this, just do one rearrangement at a time. Again, this was just one rearrangement. We're not gonna do more than one, okay? But there might be an example that we'll say later on where we'll talk about something else, okay? So any questions on these rearrangements before we move? Okay. So let's move to the workbook and we're gonna answer these questions. Okay. So depicted below are these structures labeled A through F, and we're gonna circle the molecules that undergo some sort of rearrangement, and then when they go through this rearrangement, you know, what is the specific mechanism? Is it a hydride shift? Is it an alkyl shift? Or is it a ring expansion? Okay, so let's first imagine, you know, subjecting these reagent or these starting materials to HCl. So that means that would put a carbocation on the more substituted position. So that means I would put one here, I would put one here, 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 and here. Okay, so this is a secondary carbocation. If I were to, you know, maybe move a hydrogen over or move a hydrogen over from this position, would that change the substitution? Would it change that number? And by number, I mean secondary, primary, tertiary, any of those things. So if I were to move it over here, it would still be secondary. If I were to move it over here, it'd be primary. So no, there is no increased instability that would result from any of these shifts. So no, definitely no rearrangements here, none, okay? So for B, okay, let's look next door. I'm at a secondary position right now. I could move a hydrogen over to go to the primary position, but that's like stupid. Why would I decrease stability? And I do see a hydrogen here. I could potentially move my hydrogen over, and that would make it a tertiary carbocation. Okay, so that's good. We definitely want secondary to tertiary, and this would definitely work, and it would take the form of a hydride shift. And we talked about why hydride instead of an alkyl shift, because it's easier to move a single atom than a whole group of atoms. Okay, so C, we have a secondary carbocation here. We could again move it to the right and then get a primary carbocation, but that's not going to help any of it at all. And then we see, over here to the left, we don't have any hydrogens, but we do have 3 methyl groups. So what I could do is I could move the methyl group over, and that would make it a tertiary. Okay, that works. So this definitely rearranges. And since there are no hydrogens next door, we're going to call this an alkyl shift. Okay. And then in D, we see that we have a carbocation out here. Okay. And this is a very characteristic example. Okay, and you can also tell in E as well that the only way that you can have a ring expansion is if you have a 4, or it's every time. So, you could actually memorize this, even though I hate saying that word memorize, but there's a 4, if you have a 4 or a 5-membered ring, okay? And you have a pi bond that is directly adjacent outside of the ring like this, it's always gonna expand, always. So these are the 2 classic examples, D and E. Yeah, they can be more complex, let's say, look at C over here. I don't know if you can kind of see that at the end of your screen. But, the same exact orientation, a 4-membered ring with an alkene, 1 carbon removed. That's the telltale sign of these things. Okay, so anyway, we see we have a 4-membered ring with an alkene here. Oh, I can definitely break a bond here and push it over there to make a 5-membered ring. So yeah, this is definitely gonna work, and it's gonna be a ring expansion. Okay, and same thing for E. We have a 5-membered ring and a 6-membered ring is ideal. So this is definitely going to expand, and we have an alkene outside. So another ring expansion. Okay. So for F, we already have 6-membered rings, and I don't see a pi bond outside, so definitely no ring expansion here. So I would expect a tertiary carbocation, and if I were to move it to maybe the right, that would make it secondary. But if I were to move it to the left, it would still be tertiary again. So there is really no increase in stability. So we're going to leave it at the position that's at. All right. Any questions on how I identify when rearrangements are going to occur? This is what you need to be able to do really quickly. You can first apply Markov-Nikov's rule, find that region that is more stable for that intermediate. But once you form that intermediate, ask yourself that second follow-up question, are there any internal rearrangements to make this an even more stable structure? All right, are we doing good okay? That was in English. Are we doing okay, guys? That's what it is. Exactly, tertiary is the most stable you could be. However, if there was a position maybe like tertiary resonance next door, then it would be better, okay? And we're gonna see an example in a minute, okay? Anybody else have any questions? All right, okay, so we're gonna move on to 7. For each of the proposed reactions below, draw the high energy reactive intermediate. So we know what this means. We know what these reactions are. This is hydrohalogenation. We've seen them before, but now we might have to consider ring expansions or alkyl or hydride shifts. Okay. So the first thing we want to do is, imagine subjecting this pi bond to, hydroiodic acid, and then, we develop this intermediate at the tertiary position, right? Because we have tertiary here or secondary here. We want it on the more stable position. So let's draw that structure. So this, and you guys will get better at drawing these puckered 3D structures if you guys aren't already. Okay, and then we're at this tertiary position. So I can move it to the right, and that would get secondary. I could move it here, and that would be primary, or I can move it here, and that could be tertiary. So do I see any terms of, any reason why I would shift? No, we're already at a tertiary position. This is the intermediate that I want. I'm gonna leave it right there, okay? So let's do this one. So again, we're going to subject, this pi bond to hydrochloric acid. And remember, I said anytime we see benzenes, we're going to ignore it until orgo 2. So we're going to use this pi bond, okay? And we're going to draw, maybe an intermediate that results directly from that mechanistic step. And we get, this secondary carbocation. So if we have that secondary carbocation, I see a ring next door. So definitely I'm going to expect a ring expansion. Okay, so I'm going to expect, maybe this benzene ring next to now a 6-membered ring. Okay, and if I want to count, this is important to count so you get your methyl group on the right position. 1, 2, 3, 4, 5. Okay, did I skip one? 1, 2, yep, 1, 2, 3, 4, 5. Ah, this is the 6th one. I'll do 6 right there. Okay, so that's the 6-membered ring. So let me draw those numbers in. 5, 4, 1, and now this would be, the bond is now between 4 and 3. So 4 breaks from 2 and goes to 3. Sorry, 1 second, I'm trying to visualize this bad drawing. 4, 2, 3, and then 3 is here, got it. 3 is there, 2 is there, and then that's the positive. And then on 3 was a methyl group. Okay, got it. Sorry, my drawing before was kind of all over the place with the numbering. Okay, so just let's take a moment and digest this for a second. So essentially, I numbered it like this: 6, 1, 2, 4, 5. Okay, 6, 1, 2, 4, 5 was the original. I know they did that weird, but 6, 1, 2, 4, 5. So 6, 1, 2, and 4, 5 are still here, still part of the ring. But now I'm making 3 a part of the ring. So that's why in between 4 and 2, I have 3 there. Do you guys see that? So 4 and 2 is where I broke that bond, and I'm adding 3 in between it to make it a 6-membered ring. So I should see in my structure over here 2, 3, 4, 2, 3, 4. Okay, and then on 3 we saw another methyl group, and remember we took electrons away from 2, so that's why the carbocation is now there. Okay, when you initially number the cycle out, exactly, Farah. Yeah, it's completely arbitrary. I don't know why I called that 6. Honestly, that's why it threw me off. You can call it 1, you can call it anything. It has nothing to do with nomenclature. It's just for you to get the positioning of your substituents right. How come you can't do a 1,2 hydride shift? Yeah, so I talked about this. You could arbitrarily, not arbitrary is the wrong word. I saw that before. You could do a hydride shift, and one could argue that that would be the driving force. But for our purposes of this class, and for Dr. Habenicht as well, you are only doing one rearrangement, okay? Either in the form of a ring expansion or in terms of an alkyl or hydride shift. Okay, we haven't seen an example of where we can do multiple hydride shifts yet, and I'm going to talk about the different situation that arises there. So just hang on with me. I think I have like one more example, and then we'll be at that one. Okay. So this is the structure of carbocation intermediate from B. Okay, so let's try C. So for C, we have this pi bond grabbing this hydrogen, generating free bromide. We result in, this structure. Okay, so we would think to do a ring expansion, but we said ring expansions are only to reduce, torsionals or ring strain. And we already have a 6-membered ring, so I'm not going to do any sort of ring expansions. I would rather do a hydride shift. So in this situation, I just want to move a hydride over so that my carbocation is now in the tertiary position, and I move that hydrogen there. So I don't have to draw the hydrogen in, but this would be my, intermediate. Okay, so that's what I mean by you're either going to do a ring expansion or you're going to do some sort of alkyl or hydride shift. This case looked like it was going to be a ring expansion, but we have to think twice. 6-membered rings are already ideal, so we're not going to have to reduce any sort of ring strain. So the choice instead was to do a hydride shift, not a ring expansion. Okay. Now, we're going to do number 8. So 8, the directions are down here, and it says we are going to draw the carbocation rearrangements that take place. Okay, so now this is maybe going to help some of you guys out with your issues here. So for A, right now I have the choice between a primary and a secondary position. Okay, so if I'm going to draw, that mechanistic arrow, the resulting structure is a secondary, position carbocation. I definitely see a hydride shift possible next to bring it to the tertiary position. Okay. So let's move that. So this is my rearrangement, and my resulting structure. Okay. And then we're going to have a carbocation on the tertiary, and that hydrogen moved here. Okay. Now, I actually have one more rearrangement to do. And the reason that I can do this is because each consecutive step is more and more stable, okay? So in this situation, so I would definitely start A, and I'm gonna elaborate more if it's not making sense. There is that hydrogen there again, and I can move this hydrogen in another 1,2 hydride shift, because then I get a secondary benzylic carbocation. So remember, I said this yesterday, and I know we were having some confusion about this earlier. The lower substituted resonance structure, the resonance carbocation, so the secondary resonance carbocation is more stable than the tertiary more substituted carbocation. So since each step here, let me just draw the product of this. Okay. So since each step of this reaction is going from, let's say, a secondary to a tertiary to a secondary benzylic carbocation, you're getting more and more stable. You're increasing stable, stable, again, each time. So that's why in this situation, you can do more and more and more and more rearrangements as long as each consecutive step is more and more stable. Okay, so I think for, on the key, Dr. Peterson said skip B. B I wrote, it was a bad question, so ignore it for now. There's no difference in substitution here for, in terms of regioselectivity. They're both secondary positions, so that's why it's a bad question, so just ignore that one. Okay. So before, when we were doing these rearrangements, you weren't going to do, a situation where you had a ring expansion and a shift. Yeah, it makes sense to do that. Yeah, that's what I thought when I was first in Orgo 1. Why wouldn't you want to go to the most stable every time? And for the purposes of your course, if you see either a ring expansion or an alkyl shift, you're not going to do both, okay? You're going to do one or the other, either the ring expansion or some sort of alkyl hydride shift. But if you're doing something where it's only the alkyl or hydride shift, like an example in A, you can do consecutive of that type to get to a more and more stable product, okay? So I think that is going to clarify a little bit of confusion for you guys. All right, let's do C. So for C, we have this pi bond, and this pi bond is going to grab this hydrogen and break that bromide. And then we're gonna have this intermediate. Okay. So that intermediate is gonna form on this tertiary position, okay? So am I gonna wanna do a ring expansion or am I gonna wanna do some sort of shifting? And I wanna do a ring expansion. okay? So if I'm doing a ring expansion, I'm not gonna do any sort of hydride shifts, okay? So what I'm gonna do is I'm gonna break this bond, I'm gonna put it here, okay? So the resulting structure is going to be, let's call this 1, 2, 3, 4, 5. So let's make a 5-membered ring. And let's say that this is 2, 3, 4, 5. 1, so this new bond is between 5 and 1. And on 1, I had 2 methyl groups. Boom, boom. And then remember, 2 is where I took my electrons away from. So I should expect a positive carbocation at that position, okay? And then see, clearly at this, like you could imagine moving an alkyl group over, you know, to form a tertiary carbocation. But again, for the purposes of your class, you are just going to assume one rearrangement, which was this ring expansion, and you're not going to do other versions of that, which would be a alkyl or hydride shift. Okay, so we're going to leave it there. All right, so I hope that clarified these expansion things. All right. All right, so now we're going to kind of, let me just see what else we have going on here before we move on. Could we see an example with multiple ring expansions? You will never have an example with multiple ring expansions. I've never seen that in 7 semesters of TA. So hopefully that calms your nerves. Let's do 10. I have it circled, so I think that's important. Okay, so this is a reaction coordinate diagram. And it seems really daunting, honestly, but it's not as bad as you would think. So let me just organize this again. All right, so drawn below is this reaction coordinate diagram with 1-methyl, 1-vinyl cyclopentane, and ethanol under acidic conditions. Oh, you guys actually don't know this reaction yet. Okay, let's not go there. Let's wait until we get that reaction under our belts. So let's just go to these predicted products. We're on page 63. Okay, so you know this reaction. Let's just do these really quickly. I think you guys should know how to do these, you know, pretty well now. So A through E, you guys should get 100% accuracy at this point. Okay, so what I'm going to do is I'm going to draw, you know, quickly, not the full mechanism, but I see that I'm going to have a intermediate at the secondary position. That's Markovnikov's rule. And then now, am I going to do any sort of rearrangement? That's going to make it more stable. Well, yeah, I can see I'm going to do a hydride shift. So that's going to give me a structure that looks like that. And I know my bromine is going to attach at that position. So then you can go right to your product. Okay, and did I generate a chiral center here? Yeah, because I have a propyl group to my left, an ethyl group to my right, a methyl group up top, and the bromine. So that means I would expect, you know, maybe this wedge dash in the enantiomer, and then maybe you have to include all of these, you know, stereo isomers. And then all right, can you guys hear this and see this okay? I'm sorry about that. I think my phone died. All right, sorry. Okay, so what I was saying is that we just have to draw this other stereoisomer, these two things, okay? So these are our two major products. Okay, let's keep doing it over here. So this is the whole point. For predicted products, you guys don't have enough time on your test to draw your full mechanisms. And these are quick mechanisms. You're going to have other reactions later on that take a little bit more time. So it's going to be very crucial for you guys to be really skilled at recognizing these things pretty quickly. So would A be considered racemic? 100%. Yep, racemic just means 50%, you know, one enantiomer, 50%, one another enantiomer, and since these both products do form, it is a racemic mixture. So yeah, you can even say, you know, actually at this point, you guys can't say the word racemic when you guys, I think, are done with exam 3, or yeah, it might be after exam 3. You guys can say this structure and then write racemic as a shortcut. But I think since this is the first time you guys are exposed to this, Dr. Peterson is going to want you guys to be able to recognize which are the stereoisomers. And then after that, you guys can just write racemic. Okay, so let's do HCl. So here we would expect, you know, a secondary carbocation, you know, right here. And then we don't have any hydrogens next door, so I'm definitely going to expect a 1,2 alkyl shift over here. So that's going to result in a structure that looks like that. And then we're at the tertiary position. Chlorine's going to add there. So your structure should be something that looks like that. And remember, we would expect a racemic mixture at that position. So I would draw, and then, okay, it's that easy. So yeah, seems crazy at first. I love this. I love the second half of Orgo. I think it makes a lot more sense in terms of like, just if you know the reaction and what the reagents do and their properties, really easy to kind of get any sort of question right. All right, let's do C. So for C, we're going to form quickly this, you know, secondary carbocation outside of the ring, telltale sign that we're going to do a ring expansion. So we're going to get one of these structures, and then bromide is going to add into that. So this is where she says on the key, assume one rearrangement, because, you know, you could technically go to this, you know, tertiary position, but for consistency purposes, for everybody to get the right answer on the test, and, you know, at this level of organic, you guys are just going to do either a ring expansion or those other shifts. We definitely formed 2 stereoisomers. I'm sorry, 2 chiral centers. So we would expect 4 stereoisomers. I'm not going to write them all out. You guys can write them, but you guys would know that there would be 4 products that you guys would have to pick on the test. Okay, so for here, HCl, there's no difference in substitution, so it doesn't really matter where my carbocation is placed. They're both secondary positions, and then chloride is just going to come and attack. Okay, and then this is not a chiral center, so we're just going to leave it the way that it is. Okay, so then for E, we have a tertiary position, so I would expect, you know, maybe this carbocation on the tertiary position, not the secondary, and then there's no other positioning to move around, so then bromine's just going to come in, and then bromine's going to attack, so we're going to get. Okay, now, you guys might be wondering, you know, is this a stereoisomer? And correct me if I'm wrong, did she draw 2 answers for this on the key, if anybody's following along? Does anybody have the key in front of them? Achiral. Okay, we're gonna go with achiral for this. Thank you, because there's that sigma plane. That was like the one thing I just needed verification of. Sometimes when there isn't like this plane of symmetry, like let's say these, you know, methyl groups are over here, 1 carbon over, you would have to remember that that's actually a geometric isomer, where even though you may not have, let's say, a chiral center, you would have to draw the cis conformer, the cis structure where both of them are on wedges or both of them on dashes, and then a trans conformer where there's a wedge and a dash. And let me just draw one for you guys. I think that's definitely worth noting real quick. Like I would draw, you know, maybe let's do this. Let's do a pi bond here. Give me 1 sec. I'm just going to draw this for you guys. And let me draw. Actually, I'll show this one. I like that one, and I like, let's see, this one. Okay, so structure like this. Okay, and let's subject that one to HCl. So same thing, we're going to get, you know, an intermediate that looks like this tertiary position, and we have that, and then we're going to have chlorine come and attack at that position. So we would expect, you know, there. Okay, this is not a what is it called? An achiral structure, because we don't have a plane of symmetry. So we would expect that, you know, this is a chiral center with wedges and dashes. Okay, but then we also have to consider, you know, the stereochemistry of that group, where, you know, this could be the, you know, let's say the trans arrangement, I'm sorry, the cis arrangement, because the 2 highest priority groups are on the same face, wedges, chlorine has a higher atomic number than an ethyl group, and this is just a methyl group in terms of instead of the hydrogen. So since both of these high priority groups are on wedges, it's the cis or the cis conformer. And then the trans conformer, I could just like leave that wedge the same, and I can just draw the opposite version. Okay, and that's the trans. Okay, so just that's a different type of structure to identify in terms of, we know what racemic is. Racemic's easy. Anytime I have a carbocation, I need to know that I need to draw the wedge version and the dash version. But sometimes with rings, the people kind of forget the geometric could be the type of isomer to draw. And it does say include all major stereoisomers. So just a little tidbit right there. All right. Did you guys do acid catalyzed hydration? Or you guys have not gone there yet? Yes. All right. We'll finish with that one today, and that will be it. All right. Acid catalyzed hydration. So let me just draw an example of this real quick. Acid catalyzed. So this is cool. This is how we can make alcohols. This is not the alcohols that we drink. Actually, no. Let me show you how we make the alcohols that you drink. So this structure, not this one. Okay. Do not try this at home, but this is pretty cool. All right. So we have this structure. Okay. We have, this is ethene. Okay. So it's 2 carbons. And, we're going to subject this ethene molecule to H2O and, some sort of acid catalyst. So it's not, in the stoichiometric quantities, 1 to 1. This is probably going to be like 0.0001, and that's 1 equivalent. Okay. And what it does is the reason why we have this is it probably needs a little bit of that reagent water to make it active hydronium. Okay. So we have active hydronium. Okay. So what's going to happen is this pi bond is going to grab a proton, okay? And then it's going to retain, that sigma bond density like we talked about with HBr, it's more electronegative. Let me just draw, I'm gonna take that ethanol example out of the question right now, and I'm just gonna draw this for a reason you'll know in a second. And then I have a choice, again, of where I'm putting that hydrogen. I can put that hydrogen either on this less substituted side or the more substituted side, but we're gonna follow Markov-Nikov's rule and put it on the less substituted side. So let's just say here, and that forms a carbocation on the secondary position, not the primary position. And now I just have plain water, okay? So that proton was taken up, now I'm left with just plain water. And we said earlier today in our warm-up that water is a nucleophile at the oxygen position because of those lone pairs. So then that lone pair can come and attack that carbocation, either at the front base of that unhybridized p orbital or the back base of that unhybridized p orbital, yielding a structure that looks like this, okay? It's positive because remember the formal charge of this oxygen, they like 2 bonds and 2 lone pairs, not 3 bonds and 1 lone pair. So that's why there's a formal charge. So there's actually 1 step. And remember I said there's 1 equivalent of water to about 0.001 of this catalyst. So that would mean that any excess water, which there is a lot of excess water hanging out, okay, that's not protonated, not in hydronium, can really just come back and take that proton off. And what we form is an alcohol, or maybe I'll draw it differently like that, alcohol. And this specifically is 2-pentanol, okay? I'm sorry, 2-propanol, 2-propanol. Okay, 2-propanol. So you don't know how to name them yet, but that would just be on the 2 position, 3 carbons, alcohol, okay? So it's a way to make alcohols from alkenes. Okay, so the alcohol we actually drink, if you're 21 or older, is ethanol. Okay, so ethanol would be a 2-carbon fragment. So that's why I kind of started with this. Okay, and I just wanted to draw that extra groups just to show that it was regioselective in the sense that you always form a carbocation in a more substitute position. But if you have this plain ethene starting material and you do acid catalyzed hydration, one could say that you would generate ethanol, which is, that alcohol, and that's the alcohol that's in commercial alcohols that's sold on the market. Pretty cool. All right, so let's try some examples of that. So just keep in mind that this reaction does definitely go through this carbocation, intermediate. So rearrangements are also possible. Okay, so that's why we talk about this whole, rearrangement type thing. Okay, so again, we can go quickly, I guess here. Let me do this actually. Let me draw the mechanism one more time. We just got to this, so let me just draw this on here so you guys can keep seeing these mechanisms. I honestly don't know how mechanisms are going to be tested, especially in this COVID semester, since you're not like writing on the test. Like normally we would have you draw these arrows out. So I really don't know. So maybe that's worth asking Dr. Peterson or Dr. Habenecht what they plan on doing in terms of asking mechanism questions. Okay, so you're always going to want to deal with hydronium, not just water, not HCl by itself. It's you assume these two reagents are thrown into a beaker, and whatever forms first from that is your main reagent, and this is what forms first, and that is my main reagent. So these mechanistic steps kind of seem rudimentary at this point. And we're generating a tertiary carbocation at that position. That is regioselective, not secondary, but we want tertiary. No more rearrangements necessary. And then we're left with plain water. Okay, nucleophilic, attack to that position. Okay. Oops, that was supposed to be a 5-membered ring. Sorry, it's 5. It's 5. It's 5. And here we are. And we're one step away. We have excess water hanging out based on that stoichiometric balance. And we're going to just deprotonate. And then we form an alcohol. Now, what type of alcohol did we form? Well, we formed definitely a chiral alcohol. So we need to draw both wedge alcohols and dash alcohols. So it would be these two. Okay. Got it. So it's just a different variation of it, not too crazy. So what time is it? What are we at right now? 3:50. So I'm gonna let you guys do a couple more of these examples at home. Let's just do try GHIJ. Make sure you guys get these. And let me just do one example of reaction 3. So this would be page 64. So we're here. And this is the same thing, okay? So notice how it still has an acid catalyst. It still has an oxygen-based nucleophile. But the difference is instead of just plain water, we're replacing one of the hydrogens with some sort of carbon chain. So notice how this would have been water and sulfuric acid, but we changed one of those hydrogens for that methyl group. Here, this would have been water and a proton, which is the catalyst. And instead of that extra hydrogen, we added an ethyl group. Okay, so see, nothing really drastic is changing, just the fact that this identity of the molecule is slightly altered. So what does that mean in terms of predicting the product? So let me just do it looks like L, actually, L. And we have ethanol, okay? This is our catalyst. So instead of hydronium, it really is the protonated alcohol, okay? So it's just the protonated alcohol. Remember, water, we showed this earlier, maybe back in acid-base chemistry, water plus HCl does that mechanism. Remember, don't forget any of these things. These all come back, and that forms hydronium, the protonated version, and then chloride. The same thing happens if you were to have an alcohol. So alcohols can act as, bases slightly and grab, extra protons from another strong acid and maybe make a protonated version. Okay, so this does happen as well. So notice that's the only difference that's happening. We're going from, replacing one of these hydrogens with a carbon chain. That's it. Okay, so then you can kind of imagine that the same mechanistic steps were to happen here. So that pi bond grabs a proton, it retains that electron density there. So then we have a tertiary carbocation. Now we're left with just plain ethanol. Ethanol's lone pairs are going to attack that carbocation. We're going to result in a structure that looks like that. Okay, so instead of it being 2 hydrogens, it's a hydrogen and now this ethyl group. And then finally, you have excess ethanol in solution. And then that excess ethanol is going to just remove that proton and fix that, unideal formal charge. And you are left with an achiral center, and you formed an ether. Okay, achiral. So that's your only product. So notice it's the same thing as adding an alcohol. However, it's just instead of that H coming along, it's the carbon chain. Okay, so it's the exact same thing. So I think you guys should be definitely good with your first 3 reactions. Try these extra for homework or whatever you guys want to do for practice. And I think on Friday, the material is going to be reactions 4 and 5, I believe, 4 and 5. Okay, so just make sure you guys are keeping up with the pace of the class. Like, you're going to get more and more reactions every class period, so don't fall behind. You guys are definitely good with reactions 1 through 3 by now. These videos will be on YouTube, so you guys can watch us over and over again until you guys get it. Yeah, keep working. You guys got it, and you guys can leave.